Okay, time to get started. So, last time we were talking about Stokes' curl theorem. Let me just remind you of some of the highlights. Here's the theorem, or here's one way to write the theorem. Right? And here's a way to think about it. And that is, sure, it's one integral is equal to another integral, but think about, what are the quantities that are actually of interest here? The item on the left, that line integral represents circulation. That's an interpretation that we make of when you're taking a line integral of a vector field around a closed curve. So circulation, we made the observation that circulation, algebraic though it is an accumulating quantity. It can be thought of as accumulating over the surface. That's sort of, that the curve is the boundary of. So because it's an accumulating quantity, we can write it as an integral. We worked out details on what that integrand is. The integrand ended up being this thing called curl, right? And which we interpret as a sort of a circulation density, and then there's that whole discussion about how it's an oriented density, and we don't have time to go into that whole thing again. But in an important sort of geometric point of view. Reminder again, also, we're talking about a pattern that continues to hold on this diagram. Fundamental thermal line integral says if you have a curve and you look at the boundary points, you have a function and you look at the gradient field, then that evaluation and that evaluation are the same. Gauss's divergence theorem says that if you have a solid and its boundary surface, a vector field and its divergence function, then that flux and that triple integral are the same. And what we've seen now with Stokes' curl theorem, same thing, right? But if you have a surface and its boundary curve, if you have a vector field and its curl field, then that circulation is equal to that flux. The pattern is crazy consistent, right? So keep that in mind as well. Okay. All right. Examples. We made the observation that this makes connections in the same way that Green's theorem connects to the fundamental theorem of line integrals and objects that we discussed in that context. So does Stokes' curl theorem. We talked about this idea of surface independence, totally analogous to path independence. Here's what path independence looks like. Here's what surface independence looks like. Right? It's just one dimension up, morally kind of the same concept. To be thorough, if you have two surfaces that have the same boundary curve, right? If a vector field has the property, then all such cases, the flux through the green surface and the flux through the blue surface, always the same. Wow, that's a pretty cool vector field. Any vector field that has this property that, this is infinitely many requirements. My gosh, it's for infinitely many surfaces that share a boundary, but the boundary could be infinitely many different curves, right? This is a very long list of requirements on a vector field. And if a vector field could have that property, it's a pretty neat vector field. So again, we call that surface independence, just like path independence. And we talked through how Stokes' curl theorem, which you see here and here, as pertains to the picture that I just erased. There's two instances of Stokes' curl theorem, and you notice that an upshot of this is that all curl fields are surface independent. Those fluxes are equal, and of course they have to be equal because they're equal to the same line integral. If there are two things are equal to the same thing, then they're equal to each other. Okay. All right. So again, we talked about that last time. Okay. Where we were last time is can we follow the pattern again and find a connection between Gauss's divergence theorem and objects that we talked about in the context of Stokes' theorem. So reminder. This is going to follow this pattern. So this is a conversation that we had in the context of Green's theorem. Recall the idea was that we had two things with the same boundary. Now here that shared boundary is a pair of points, and the two things are curves, or to be more careful, oriented curves. Right? With some exceptions granted of curves crossing, little annoyances that can be dealt with by means that we don't need to worry about in this class, then there is a solid region area in between here whose boundary relates to those two curves, and beware the minus sign. Well, same thing, same setup happens in this three-dimensional context. Here we, though, have, instead of two curves with the same boundary points, here we have two surfaces with the same boundary curve. But note, the punchline is the same. There is still this region in here, in between, whose boundary is relates to those two original, in this case, surfaces. Again, beware the minus sign. Now, again, just for dramatic effect, look at that picture. Look at that picture. See how they're there's a lot of analogies. Green and blue have the same boundary, so between the two of them, they make the boundary of something else. Here, green and blue share the same boundary, so between the two of them, they make the boundary of something else. It's really, really analogous. Right? So, great. Let's try to apply a theorem like we have done in the past. And I kind of got a mess here. Let's look at Gauss's divergence theorem now, as it applies to this picture. That's what Gauss's divergence theorem says. The line integral around the boundary, the flux through the boundary. There's that boundary flux. Don't forget the minus sign. Is equal to a triple integral over the interior of the divergence, straight up Gauss's theorem. And structurally, then, this formula looks an awful lot like this formula that we were talking about in this previous context. You'll even notice, by the way, on purpose, I deliberately laid it out on the page the same on both pages. You're going to even kind of lose track of which page you're on. Right? Again, that is on purpose. So what does Gauss's divergence theorem tell us? Well, let's follow it through. What do you suppose would happen if the divergence were zero? Well, if that integrand is zero, that means that triple integral always going to be zero. And that means that this other side of the equation is always going to be zero. Namely, a difference is zero, which means those two things are the same. Right? Wait a second. What does it mean for two fluxes over surfaces that share the same boundary curve? If those two fluxes are always the same, well, my gosh, that means surface independent, which we saw previously means that the vector field is a curl. And so we have a justification of one of our lifetime theorems. One of our lifetime theorems says that when the divergence is zero, the vector field is a curl. And the argument goes backwards just like it did in the other context. If a vector field is a curl, we already know it's surface independent. If it's surface independent, these two integrals are equal, which means that difference is zero. If that difference is always zero, well, unavoidably, then that means that this triple integral is always zero. How's that possible? How can you have a triple integral that's always zero no matter what R is, no matter what your domain for integration is? Well, that means that this integrand has got to be zero. Okay. All right, so going to our diagrams, we've previously talked about these two lifetime theorems. This is the old news. If you have a gradient, then the curl is zero. And if a curl is zero, then it is a gradient. Talked about those. Now, we've justified these down here. If you were looking at a curl, its divergence is zero. And likewise, if the divergence is zero, as we just argued, that means there must be a vector field for which it is a curl. Okay. All right. So I like this argument because it gives you a geometric sort of perspective on, it's one thing to know that something is true, and it's another thing entirely to have an intuitive sense for why something should be true. And I think that's what these arguments here give. So that's what I like to talk about. Okay. All right. So, quick summary then of things we've talked about in the last 5 minutes, 10 minutes, I guess it's been. We talked about first this idea of surface independence. Surface independence says that under certain circumstances, you could just rewrite one flux as a flux over a totally different surface. Wow. Right? Rewrite a flux over one surface as a flux over a different surface. Neat trick. When can I do this? Well, I can do this, among other things, when the field is a curl. How do I know? How do I know if a field is a curl? Can I just look at a field at a glance and decide, hey, that looks like a curl to me? Right? No, we don't have that sort of a sense. So how do you know if a field is a curl? If the divergence is 0, the field is a curl. So that's how we're going to use, that's how we're going to capitalize on this collection of ideas. Take the divergence of something. If you get 0, that means your vector field is a curl. That means that your vector field is surface independent, and that means that you can just change your surface to your preference, preserving the boundary, of course. Okay. Alrighty, so let's see an example of that. Hard problem. Here's a vector field. Whoops, I wanted to change the color. Here is a vector field. Here is a surface, and here's a picture of the surface. I mean, it's it's a curved, highly curved surface, upside down paraboloid. The part of this paraboloid that's above the XY plane. And given that surface, given this vector field, I would like to compute the flux. Now, let's consider options. What can we do here? How do we compute fluxes? You can parameterize. Totally. You can do that. Parameterize, pull back, plug and chug. It's not very pretty, but you can do it. Okay. Let's see here. Can we use Gauss's divergence theorem? Gauss's divergence theorem allows us to compute fluxes sometimes, right? There it is. There's a flux that you can compute with Gauss's divergence theorem. Problem. In order for this to work, notice that my domain must be a boundary. That's what the theorem says. Certainly it's what the diagram also indicates. This only computes boundary fluxes. And our surface here, where am I? What did I just do there? I'm sorry, I'm on the wrong, okay, somehow that got into the wrong screen. Okay, fine. So here, is this surface, is that a boundary of something? And no, it's not. This is a cereal bowl upside down. And I claim if you take a bowl of cereal, right, if you turn it upside down, cereal falls out. Right? So now don't make the common mistake. A lot of students would like to say, it feels like that this surface isn't it a boundary of, isn't that surface the boundary of this? And no, it's not. It's part of the boundary of that, but it is not fully and completely the boundary of that blue solid there. The reason why the boundary of that blue solid is what I'm about to do in green here. The boundary of that blue solid is, it's the whole yellow thing, but then also the boundary of that blue solid includes this piece on the bottom. It includes this part of the XY plane. Right? That's not part of our surface. To which sometimes students will play, well, yeah, but kind of isn't it though? Because look, it says right here, z greater than or equal to 0. Can I just sort of take the z equals 0 part? Very much not. Do keep in mind, what this says is we're looking at points that are on the surface, on this paraboloid. which satisfy a further requirement. So this is a way of telling you what part of this surface you're interested in. It is not saying, yeah, and also whatever part of the plane z equals 0 you might happen to find convenient for your purposes. That's not what it's saying. Right, now, let's just go, we're on a little bit of a digression here, but is everybody clear now that this surface here, described like this, is definitely not a boundary of a solid? Everybody on board? Okay. All right. Okay. So yeah. So the theorem. Actually, why don't I? I'm sorry. This got where it wasn't supposed to be. This is supposed to be down here. And, okay, so that's, what? Okay, sorry, this keeps taking me to the wrong page. I guess I'm here now. Okay, fine. Okay, so, we can't use Gauss's divergence theorem here because, it's not a boundary. Gauss's divergence theorem says you can compute fluxes of boundaries. That's not us. Okay. All right. What's our other option? Hey, let's consider the possibility. Maybe we could use Stokes's curl theorem, right? I mean, Stokes's curl theorem allows you to compute fluxes. Right, there it is. Compute a flux. It doesn't even have to be a boundary. This says any surface. Yeah, I've got to be able to take that surface and I've got to be able to compute its boundary curve, but I'm not scared of that, right? Look at this. I can find the boundary curve of this surface. No big deal. The boundary curve of that surface is that thing. No problem. Right? So there is a temptation to say I can use Stokes's curl theorem. Here's the problem. Here. Your integrand has to be a curl of something. And more to the point, even more importantly, I need to be able to find that anti-curl, this thing here, this f, whose curl is my integrand. I need to be able to find that because it is my integrand of my resulting line integral. So I've got to be able to compute what I like to call an anti-curl. Can I compute an anti-curl? Did y'all notice I've never showed you how to compute an anti-curl? And the reason why is it's hard. It's beyond what we can reasonably do in this class. So it's not a tool that we have at our disposal. So just, directly with no additional information given, computing anti-curls, not something we can do. So we've got a crash and burn there, too. So neither one of these boundary theorems works. Again, it remains that we can parameterize and plug and chug, do the pullback and plug and chug. That's a lot of work, and again, we're hoping to find a way around that. Okay, so divergence theorem, directly applied? No. Stokes's curl theorem? Not really. So what do we do in this circumstance? And the answer is we use surface independence. As it turns out, lucky break, this happens to work. The reason I know that I can apply surface independence is because my vector field, my integrand for my flux, I can compute the divergence of it, and I get 0. And as we discussed, if the divergence is 0, that means it is a curl, and if it is a curl, it's surface independent. Okay. All right. So, knowing that it's surface independent, I get to make the following wonderful choice. I get to take that surface that we were given, which I don't like because it's curved, right? And, awkward, right? I get to take that surface and say, phooey on that, I like this surface here better. That surface there, it's got the same boundary. Got the same boundary curve. And so due to surface independence, I can just say, phooey on the yellow surface, I'm going to choose instead this green surface. By surface independence. Everybody on board? It's all downhill from here. This resulting integral over this green surface S2. Oh, you know what? Let's be careful about orientations. Our original surface was given oriented this way. It is because our original surface was oriented that way that our boundary curve was oriented that way. Think it through. Thumb, swirls, side swipes, right? That's a nice exercise. Confirm for yourself that that's the way that goes. And with that oriented that way, now I've got to decide, does my orientation on my new surface, does it go that way or this way? And again, thumb, swirls, side swipes, think through the options, and it's got to be this one. Right? So you can't just assume, you can't just, this one was oriented in a way that seems generic or right or something, right? You've got to play the game and think about the induced orientations. Okay, so we've got this new surface, and that surface is real easy to deal with because it's flat. The ds vector is easy to understand because that N2, you can see it right here, that N2 vector is just 0, 0, 1, right? And 0, 0, 1 is really, really easy to dot with this vector field. It's going to just pick out just that third component, xy. And so altogether then, we get just integral of xy, and by a symmetry argument, that integral 0. So really nice argument, right? You take computationally speaking, you take the divergence to establish surface independence. Make a clever, appropriate choice of your new surface, and then capitalize on all the benefits of that new, clever surface that you chose. Okay, last thing I'm going to say about surface independence before we go on is about why you should care. Let's go back to path independence. Path independence happens when the vector field is a gradient. And we know how to find anti-gradients. And any time that you could use path independence, computationally anyway, anytime you could use path independence, you could just use the fundamental thermal line integrals, which is pretty cool. And so, do you really need path independence? And I made a case about how, math is not about just turning cranks and computing things, right? Path independence serves a conceptual role, right? That's what allows you to motivate ideas like conservation of energy. I won't get into that whole thing again. But that said, from a computational perspective, path independence, vast majority of the time, I'd probably just use the fundamental thermal line integrals. Right? So, case could be made here. Isn't that going to be true here? We've got so many patterns. Why didn't that pattern hold? The reason that pattern doesn't hold is because path independence, yes, quite right. I have simultaneously the option of using the fundamental thermal line integrals, and I know how to compute anti-gradients, and let's do it. But for flux integrals, yes, I suppose Stokes's curl theorem is an option, but remember, even though I know that anti-curl is there, I don't know how to do this in the context of Math 212, right? So the argument that I have there in blue, outlined, sketched in blue there, computationally speaking, yeah, sure, path independence, I don't really need it. Surface independence, we desperately need it because we don't know how to compute anti-curls. So anyway, keep that in mind. This surface independence thing is a powerful computational tool in circumstances that arise often significantly and for which we do not have other good options. Okay. All right. I'm going to say some quick things about physics, but not a whole lot of time on this. So here's the first thing I'll say. Suppose you have current in a wire, let's say going that way, and y'all may have had a physics class in the past. You may be aware that current creates a magnetic field. It just does. That's the way this place that we live happens to work. I don't know why. It's just that's the way the world's put together. Okay? So let me draw a magnetic field. A magnetic field kind of wraps, if you will, sort of around Kind of like that. And by the way, the order, we've got a two-dimensional picture here, and it's easy to kind of see this backwards. This current, the induced magnetic field is supposed to go around like this with the right hand, right? It's easy to see it in either of two different ways, kind of in an Escher sort of, the picture pops. But this is the way that I'm intending. Okay, so it's this fact about physics is not just for current in a wire. This is also true of what we call a current field. In other words, in the same way that water can flow in a pipe, or water can just kind of flow like in the ocean, right? Likewise, charged particles can flow in a wire, or the charged particles can just kind of flow like in an ocean of charged particles, right? Like a fluid of charged particles, right? So, in that circumstance, this flow that we represent with a vector field, as of course we often do, we call this the flow field of charged particles. Sometimes this is called the current field. Right? That creates a magnetic field as well, and it analogously kind of goes, if you will, sort of around the flow like that, right hand rule, and it's not a physics class, so don't worry about it. So what is the relationship between this current field that I have in yellow and this magnetic field that I have in purple? And the connection is very, very conveniently by way of curl. So given a flow field, by the way, this does have to be a steady state flow. Everything gets different and complicated when it's not a steady state, like if the current is in the process of increasing, or if the charged particles are accumulating somewhere, something like that. Everything's different, but so steady state only. But the resulting magnetic field relates by way of curl. All right, so a couple different ways to think about this. Here's one of my favorite little observations here, and I'm going to be very quick with this because, again, this is not a physics class, but I do think this is a nice observation. There is a way to think of a physical process that will do this job for us that we were complaining about our inability to do. How do you find anti-curls? How do you find that anti-curl field? And here's a physical process. Think of the current. Think of the vector field that you want to find an anti-curl of. Think of that as being a current. All right, so we'll go over here to here. That vector field. Think of it as being a current. Fine. Okay. What happens when you have a current? Well, as we just discussed, currents, the physical universe constructs for us the resulting magnetic field. Again, that's how the world works. You make a current, there is a magnetic field that will just generate. Right? Thank you, universe. And by the way, interestingly, that field that gets created, that is the anti-curl. Purple. Right? That is the B field. That is the field whose curl is our flow. So I think it's a neat observation. There's something really satisfying about that the physical universe generates for us the anti-curls that I claim exist and that we algebraically don't know how to compute. Yeah, anyway, I just think that's fun. Okay. All right, moving along. I need to talk about Maxwell's equations again. Y'all may recall that there are 4 Maxwell's equations, kind of, depending on how you count. This is what I'm going to call Maxwell's equations numbers 3 and 4. So this is number 3 and this is number 4. Remember, the first 2 of Maxwell's equations were about the divergence of the electric and magnetic fields. The last 2 of Maxwell's equations are about the curl of the electric and magnetic fields. The reality is these. The curl of the electric field is the negative time rate of change of the magnetic field. Don't ask me why. That's a physics thing. It's why is the universe? I don't know. Is it physics or is it philosophy? Right? It just is. Right? And then the curl of the magnetic field is, as we just saw, proportional to the current field. Okay. All right. So why are we talking about this in the context of Stokes' theorem? Well, because there are different versions of these equations. These are what we call the differential versions, because you can see right here it involves derivatives to state them. Right? Curls are derivatives. There are integral versions of the same theorems, and here's how that argument goes. I guess I do have to, let me zoom out a notch so we can see it all on the same page. This equation here, what I'll call the differential version of this equation, there it is, differential version. Just take the flux of both sides of that equation, as I've done there, and notice then that what I get is this equation, which I sort of recopy the other side over here, that says that the electric current is equal to the circulation of the magnetic field. Okay. All right. And I call these two different versions of the same equation because they're really talking about very similar things, and they're so easy to connect to each other. Very strong analogy with how we did this when we were looking at the first two of Maxwell's equations. So, a little bit different story, but morally equivalent. So, here's one way to say this. The integral version here is about current and circulation. The differential version is about what you might call current density, because that's the flow field. That's the thing you take the flux of to get current. So current density and flux density. So, I'm sorry, and circulation density. Sorry. I said that wrong. Let me say it right. Sorry about that. I had my wires crossed. This is about current and circulation. This is about current density and circulation density. Oriented densities, of course. Okay. All right. So these two different versions, these are called the integral versions. Again, no surprise that I call these integral versions because, look, they involve integrals, right? Two different versions of the same equation. So again, this the way you might say it then is that this is Maxwell's third equation, and this is Maxwell's fourth equation. Yeah, there's two different versions of each one. Morally the same theorem. Okay. Last observation. Why do we talk about this in the context of Stokes' theorem? Well, because Stokes' theorem is the thing that allows you to make this connection. This is the necessary tool that allows you to rewrite that flux as a circulation. So Stokes' theorem is that which makes it easy to see how to connect these two different versions of the theorem. Okay. All right. Okay, there is an example on the next page of the notes. We are going to skip this example. It's just an example. It's kind of supplemental. This is not something you absolutely positively have to know. On the other hand, if you are majoring in engineering or physics or even chemistry, it'd be a pretty good idea to look at it. It's a straight-up application of this formula, right? No big deal. Give it a look. But we don't have time to talk about it here. Again, it's supplemental, so we're not missing anything critical. Okay. So we are kind of done with new material in chapter 15. Everything that follows here is just kind of summary and review and kind of bringing everything together. Some ideas I like to talk about, but we've covered all the new material, so that's good. So the reminder of what have we been doing. These are, I guess I better zoom out. Various different theorems that we've talked about. Recall, we've talked about all of these different theorems. Fundamental theorem of calculus. Well, we reviewed it. Fundamental theorem of line integrals, kind of twice, right? There's an R2 version and there's an R3 version. Whatever. Green's theorem, Gauss's divergence theorem, Stokes's curl theorem. All right, all different theorems, but they all follow the same pattern. And that's very important. Okay. All of these theorems compute a quantity. Now this is not really how we've in the past thought about the fundamental theorem of calculus, but this is the way I'm encouraging here for this purpose. Think of the fundamental theorem of calculus as computing change so that, for the purpose of setting up a template that allows us to have a way to think of all these other theorems and what they compute, right? Fundamental theorem of line integrals is a statement about an accumulation of change. Green's theorem is a statement about an accumulation of circulations. It's a different accumulating quantity, still an accumulating quantity. Gauss's theorem is about the accumulation of flux, and Stokes's theorem is about the accumulation, again, of circulation, kind of like with Green's theorem. Okay. All right, so in all cases, these theorems are computing an accumulating quantity. Okay. Accumulation means you compute it with an integral. Integrals have integrands. Here are what those integrands were. Right? You all recognize these straight out of the theorems. Right? And it's just formulas. But what I want to call your attention to is that because we're looking at quantities, or here, let me do it like this. Because we're looking at quantities, accumulating quantities, and computed as integrals of corresponding integrands, each one of these things then is an associated density as appropriate to the quantity that's being computed. Okay. All right. So I'm a big believer in analogies and comparisons and sort of back and forth connections. To whatever extent you feel like maybe you've got a good intuition for the fundamental theorem of line integrals, keep in mind that then is a tool that you can use by analogy, extending appropriately where necessary. That's a tool that you can use to help yourself understand, for example, Gauss's divergence theorem. There's different operators, different objects, different kinds of boundaries, different conventions on orientations, blah, blah, blah. Right? A lot of differences, structurally a lot of similarities. So keep that in mind. Okay. So don't forget the patterns we've talked about. All of the theorems. I'll be quick with this. All of the theorems involve taking a boundary of something, applying an operator to something, and then looking at the appropriate evaluations, plugging in the things that you've just created, and you get two things being equal to each other. Right? So make sure to remember that pattern. There are some special objects, special integrands that we've talked about. I want to remind you, again, just to see the patterns that are going to develop. Some special things that we've observed. There are some special vector fields, for example, in R2. Let me remind you about what were the special vector fields in R2 and what makes them so special. The special vector fields are those that have, all three of these properties, all three of these equivalent properties. Let me just emphasize these are equivalent. Okay. So what do they say? First, gradients. The special vector fields I want to talk about are gradients. There is some function whose gradient is that field. Okay. Yes, but those same vector fields are also vector fields for which Green's operator is 0. Okay, so these same vector fields, Green's operator is 0. And these same vector fields, and this one's a little hard to draw a picture of, these same vector fields are path independent. Here's how I'm going to draw path independent. I'm going to zoom in. It gets weird. A vector field is path independent if when you have two curves with the same boundary points that the line integral is the same on both. All right, so it's just a figurative way to represent it on the picture. Okay, but these vector fields that I'm talking about have all three of these properties. Any vector field with the yellow property also has the green property, also has the blue property. That's pretty special to have all three of these simultaneously. Reminder, one of the big disclaimers of all of this is that every function and vector field in sight has to be continuous and differentiable, and there can't be so much as even a single point where something is undefined or everything crashes and burns. So I don't want to deal with those kinds of difficulties right now. But anyway, that said, these are three different shared features of these same vector fields. Okay. All right. That pattern holds in R3. Vector fields that are gradients are also vector fields, well, not Green's operator anymore, but vector fields for which the curl is equal to 0, which are also vector fields that are path independent, and therefore any two curves with the same boundary points give the same value of the line integral. So same connection holds the special vector fields, gradients, irrotational, path independent. Okay. So same pattern. Really, really similar. The pattern continues one dimension up, and this is where it gets a little bit of an eyebrow raiser. Same pattern holds one dimension up in R3. There are vector fields here that are special. They are vector fields that are curls of something. They are vector fields for which the divergence is 0. They are vector fields that are surface independent, namely, anytime two surfaces have the same boundary curve, the resulting fluxes are equal. Notice how that little diagram chase, figurative representation on our diagram, the special fields, you might say, let's talk about them as the curl fields. Curl fields have a list of properties that are super analogous to those of gradient fields, just one dimension over. Right? It's the same properties, just shifted. Yeah. Okay, let me put that back. Okay. All right. So keep all that in mind. Alrighty, now let's talk about computation. After all, that's one of the big things that we do in this class is we compute stuff. How do you use these all these theorems to compute stuff? There's a pattern. I want to encourage you all to use this pattern as much as possible. So it's all about using the diagram in the most sort of convenient way. So step one, figure out what have you been asked to compute, and where does that show up on which diagram. So figure out where you are, right? So, for example, if the question asks you to compute a line integral over a curve in three-dimensional space, okay, well, they asked you for a line integral in three-dimensional space, so this is what you're trying to compute. Right, so go ahead and, just think to yourself, identify that on the picture. Okay. All right, next thing to do. Notice then, what are your options for using one of these boundary theorems, accumulation theorems, density theorems, however you want to call them? Which two are on the table? So, for example, here, if we're trying to compute a line integral in R3, your candidates are fundamental theorem of line integrals, right? Hey, maybe I can do this, find an anti-gradient. The other candidate is Stokes' curl theorem, right? Maybe I can compute the curl. And find an anti-boundary. Okay. All right. So, more to the point, maybe I can turn that into a flux integral. So, those are your two options. And now, with this in mind, let me reveal. There's a point of view that I have, and I think a lot of the people that grade for this course will have the same point of view, which is if the question involves computing a line integral, if we see divergence anywhere on the page, this is not good. That this student has no perspective on what line integrals are and what theorems relate to it and what anything has to do with anything. That's a really bad sign if divergence is so much as even on the page. Right? Now, some students strategically think, I'm gonna try to answer this question shotgun style. I'm gonna throw out every single object of multivariable calculus that I've ever so much as heard of, and I'm just gonna write it all down in the hopes that part of it'll be right, and that I'll get partial credit for at least that part was right. Okay, we're very well aware of this strategy. That does not communicate understanding, right? And so you're not going to get points for that. So don't waste your time with the shotgun style strategy. It's kind of morally akin, if you think about it, to on a multiple choice question, checking all 4 of the options, thinking that, hey, one of them's going to be right. Right? Doesn't make any sense, right? From a grading standpoint, doesn't make any sense. So yeah, don't write down something that's completely out of the realm of possibility for your question. Likewise, no triple integrals. There's no triple integrals that have anything to do with computing a line integral. It's just not gonna come up. Okay. All right. So figure out what your realistic options are and think about those options. Do what the diagram says and compute the appropriate operator. Now, what is the appropriate operator? Here I've been asked to compute a line integral. I therefore have a vector field that is my integrand. What is the diagram telling me to do? For this vector field in that position on the diagram, the diagram's telling me compute the curl. So go ahead. And keep in mind, there's a couple of different possibilities of how this might come up useful. If you compute the curl of this vector field, if you get 0, you know that there's an anti-gradient, and now you can use the fundamental theorem of line integrals. That's one possibility. The other possibility is that you don't get 0, in which case there is no anti-gradient. You can't use the fundamental theorem of line integrals. Then Stokes' curl theorem becomes your, fingers crossed, I hope this works out, leading candidate, right, for being able to use one of these theorems. And note, Stokes' curl theorem will require you to know what is that curl. So case could be made that either way, it's useful to know what the curl is. So go ahead and compute it. I don't want to say it's a no-lose situation, but it's going to be useful one way or the other. Yeah.
What's the difference between the fields under 1 and the fields under 2?
Oh, well, yeah, it's just a context thing. So these numbers here, this is what you're asking about, is that right? Yeah. These refer to the dimension of the domains that we're looking at. So, for example, in this 2 column, we're looking at integrals on surfaces, and surfaces are 2-dimensional. It's just sort of to organize things. Yeah, that's all. Yeah. Okay. So, compute the appropriate operator. And now, that'll lay out your options for you. Do be aware, of course, it is entirely possible that neither theorem will apply. Right? Maybe there is no anti-gradient. Maybe the curve does not have an anti-boundary because the curve isn't a closed curve. It's just not a boundary of anything, right? It just isn't. And if that's the case, if neither one of these theorems applies, then you're back to kind of square one. Oh, not exactly. I mean, you do have these other options. It's possible. Path independence, maybe. Just always keep that in mind. Every so often you get geometrically lucky, right? We saw some instances where it just happened to be that the vector field and the tangent vector were always perpendicular and the dot product's 0. Cool. Symmetries, you might get lucky. So always kind of keep your head on a swivel. Sure. Right? But, I'm going to lay out all your options at this point and then, pick whichever one you think is going to be the least work. All right, so I have some examples. I guess I have 30 seconds for 6 examples. That's not going to happen. So we'll finish these up next time. One last suggestion I want to make. So these diagrams here. So there's this one here, and then there's the analogous diagram in R2. I have a suggestion for you. I hope you will follow. I hope you will take me up on this suggestion. It's going to sound outrageous and implausible. I encourage you to memorize this entire diagram. Now, before you before you reject the concept entirely, you may have already memorized it inadvertently. Okay, don't forget, there's just tremendous patterns here, right? Here's all you really have to memorize is what order do these operations go. That's really the only thing you have to memorize. Everything else, I challenge you to forget it. All right? If you've been, paying attention in class, right? What have we been doing to vector fields on surfaces? We've been computing fluxes over and over and over again for the last several weeks. Of course, fluxes are what you do there, right? Likewise, what have we been doing for vector fields on curves? We've been computing these line integrals over and over and over again. These theorems down here, it's the pattern, right? I guess technically you have to memorize this pattern. It's a pretty easy pattern, and again, we've been doing it a lot. You've been seeing me make that sequence of marks for weeks now. So you may have already memorized that pattern. What do you write down? Well, what do I write down there? Well, it's a flux of a curl. You don't have to memorize that. The pattern you've already memorized tells you what to write down there. Right? And all this stuff down here, lifetime theorems. Again, everything has a lifetime of 2. It's has several different looking consequences, but it's a pretty easy pattern. Okay, so not much to actually memorize. That said, I encourage you to put in the couple of minutes to memorize those last couple of bits, and the challenge to see if you're ready, to see if you've successfully memorized this is, spend all the time you want looking at it, thinking about it, noticing the patterns, etc. And when you think you're ready, put it all away, take out a clean sheet of paper, and reproduce the entire diagram down to the little micro details. That'd be a fantastic little test, and also gives you a very powerful tool that you get to use for free on the exam. So, the midterm exam and, of course, on the final exam. A lot of students choose to, as soon as time starts on the exam, step 1, you turn over that back page and write the diagram. And now you've got an unfair advantage. Or you don't have to write the whole thing, but maybe write down just, a couple of key points or something. Anyway, for your consideration, y'all have a good day. See you later. Again, if you came in after I started going, let me make sure to get you down on the attendance.